I would like to welcome you, first of all, and thank you for joining today. We have a very interesting topic from the power electronics domain, which is the role of passive components in efficiency power electronic systems from theory to live LTspice simulation. And I would like to ask you to turn off your camera and mute your microphone if you're not raising a question. And if you have a question, I would recommend to start typing it in the chat. We have a live chat during the webinar, so the speaker can see your question and can approach it right away. And we have also prepared a survey in the live chat. And we would like to ask you also to leave your comment there to give us a little bit more information about your background. So we are asking about your past experiences with LTspice in order to be able to shape the webinar in a better way. And I would like to start with a brief introduction about WiredWide, what we do and why we do it. What is WiredWide? WiredWide is a engineering platform developed by engineers for engineers. So we have this ideology or vision of having a full cycle engineering, meaning you are starting, let's say, your journey as a typical engineer at the university or engineering school. At this time, you're most probably a customer of ours of the WiredWide platform, meaning you are a student and you're looking for help with your let's say bachelor thesis or master thesis or even a PhD work or project that you're running or you're finishing. So based on this need and request, you can take a private tutoring and mentoring using our platform from one of our experienced partners and tutors. You can take online courses using our platform. So we offer a lot of engineering courses online. You can study based on these courses. These are in the field of computer aided engineering, mostly computer aided design, CAD, or FEM, FEA, or CFD analysis. So these kind of courses that we are um, releasing, distributing, and offering to our students to get yourself, let's say, up to speed to the state of the art technology and computer aided engineering software tools to get this knowledge. We have also the knowledge base. We have technical articles. So as a, let's say, less experienced engineer, you can read those articles. You can read the technical reports that we have from our previous projects that our partners share with us or with our customers, their experiences, their insightful information, how-tos from the field of engineering, from using different engineering tools like SolidWorks or like CAD tools like Fusion from Autodesk or any other basically engineering tool that they're using. They are sharing their experience with that. They're sharing insightful information, and you can read these reports in the form of technical article on our platform. It's available for free to every user of the platform. And once you gain some experience as a student, so basically you're going through that maturity phase, and you are becoming an engineer, an experienced engineer yourself. You can, let's say, transition to a partner that we call our second type of user role is the partner as a role. And as a partner, you can, using our platform, you can provide tutoring. You can provide the mentorship to students or to industrial customers, to companies, being a, let's say, advisor or a freelancer or a contractor. You can obviously be a content creator. You can create and host on our platform your online courses, and you can sell your online courses using our platform. So we provide the um, online course tools for that, to host it, to set it up, to create some videos, to attach some quizzes, to educate your students, and to sell it as a course, as a digital product, as an e-commerce product using our platform. So we provide all the necessary instruments to be able to do so. And of course, as a freelancer, you can join an industry project together with the team from industry, from a company working on some particular task, on some industrial project, on some technical challenge that the company is having currently. You can support that company that is at the same time on our platform as a joining as a customer, and you as a partner can join such an industry project, and work together with the company, with some businesses, with some development teams from different companies, solving a particular engineering task. For instance, creating some model, some CAD drawing, or supporting with some finite element analysis, or supporting with some computational fluid dynamics, or supporting with some power electronics simulations, like in LTspice or Eagle, or any other power electronic software tool like SimScape or SimPower Systems from MATLAB, from MathWorks. So you can basically do that as well. And the circle is closing in that way. So that is why we call it full cycle engineering. So basically you're starting from the beginning, using that as a, let's say, a technology enabler, knowledge sharing tool, instrument, and you're finishing or ending up using the platform as a freelancer, or as an expert, as an engineering, let's say, unit, and you provide your own services and monetize your own skills and knowledge using our platform. And we provide also all the necessary instruments to do so. And I would like now to switch to our today's speaker to introduce Anne. So Anne Vilasingon-Dagani is the power electronics engineer with experience in electric vehicle applications like onboard chargers or DC-DC converters for high voltage architectures and applications. For instance, 400 volt DC or 800 volt DC. She has worked with leading automotive tier 1 suppliers, including Valeo and Panasonic Automotive Systems. Anne as well worked with Volvo before, contributing to system design and pre-development activities and requirement engineering. And she's currently together with Geo Group, where she continues to work on these topics and on advanced power electronic applications. And she supports the customer-oriented solutions with global OEMs. So welcome, Annie. Thanks for having a speech today, for giving us the topic explanations and also the live demo in LTspice. I'm looking forward to that. You can take over now and you can start the screen sharing on your side.
Yeah. So can you please confirm if you can hear me well and see my screen?
Yes, we can. We can
Okay.
see and hear you clearly. Yeah.
Okay, so good evening, everyone. First of all, thanks for joining this webinar. In this webinar, I will start with the fundamentals, so what an onboard charger is, and then give you an overview of how you charge an electric vehicle, and then we'll work our way through the charger itself, block by block, the various passive components present inside it, And along the way, we'll also touch a little bit on the wide bandgap semiconductors, which is a hot topic right now. And we'll see what are the emerging trends and where the technology is heading. And we'll also have an LTspice simulation towards the end, demonstrating an EMI filter. And then we can open it up for your questions. So starting with an onboard charger. So what is an onboard charger? So when you see an electric vehicle on the road, so you know that it's not running on fuel, not on diesel or petrol, but it has a battery, which a high voltage battery, which is powering the car. So this high voltage battery is normally needing a DC voltage, but when you are charging your electric car, so you get AC from the grid, so which is not suitable to charge your battery. So there is a component inside your car, which is called an onboard charger, which does the power conversion. So basically, in simple terms, it converts the AC voltage from the grid to charge the battery with a DC voltage. So before we go inside the charger itself, so here is a quick overview of the different types of connectors that are present in different markets. So on the left, you can see the AC connectors. So these are normally going through your onboard charger. So they are called type 1, type 2, and NACS, which is predominantly used in the North America. This is introduced by Tesla. And on the right, you can see DC fast charging connectors, which is bypassing the onboard charger, so which is not so much relevant for us today. So here you can see different connectors. Which one you see depends on where you're located. For example, the type 2 is very popular in Europe and NACS is very popular in North America. So this NACS stands for North American Charging Standard, which is originally Tesla's charging station. It is a special kind of connector because here you can have both AC and DC voltage on the same pin. So it's something different when compared with the combo connectors, because here you have separate pins for both AC and DC. But the Tesla's charging connector is much lighter because they use the same pins for both AC and DC. So for today, just remember that the AC goes through our charger, the onboard charger inside the car, so we can skip DC fast charging. So let's talk about the charging speed, because normally there's a common misconception here. So when you take a car with a 60 kilowatt hour battery, so when you talk about an EV, it's very common that you talk about the rating of the battery that you have. So on AC, normally the power is the voltage times the current. But here's the key, because the onboard charger's own rating becomes the hard limit. So assume your car has a 3.7 kilowatt charger and it runs on single phase. So from the AC grid, you get 230 volt and it draws 16 amps per phase. So it's taking more than 17 hours to charge your car, fully charge your car. But when you go to 11 kilowatt onboard charger, which is having 3-phase and drawing 16 amps per phase, so you can charge your car under 6 hours. So same is with the 22 kilowatt charger, you're increasing the power and the charge time is less than 3 hours. So how do you get more power? So there are two ways. So normally you can increase either your current or you can increase the number of phases. But let's assume that you have a car with a 3.67 kilowatt onboard charger and you want to charge your car faster. So you go to a charging station which has higher power. So even though you go to a charging station with a higher power, you simply cannot do it because you are limited by the rating of the onboard charger which is present inside your car. So here you can see a 3.7 kilowatt onboard charger plugged into a 22 kilowatt wall box will still charge at a slower rate because you have a smaller OBC. So if you want to go faster on AC charging, then you need a bigger OBC, which is going to cost the size, weight, and also additional money inside the car. So now talking about efficiency. So here, what happens when you charge your car? You can see on the display that if you have a 11 kilowatt OBC, you can see that normally you are not always charging at 11 kilowatt. It is somewhere around 10.5 to 10.9. So where are these? Where do the watts actually go? So this is the number that I want you to notice. So roughly around 38 percentage is lost in the passive components inside the charger, which are mainly the magnetics and the capacitors, and not really coming from the active components. So why does this matter? So your customer wants you to design an onboard charger, and they give you a number for efficiency. So they say, I want a 96% efficient onboard charger. So when you do the calculation of 96 percentage of 11 kilowatt OBC, you see that you're losing around 460 watts as heat. So when you want to improve your design and you just add 1% more to the efficiency, you can see that you're saving around 115 watts. So this is a significant saving, which means you can save some cost on the cooling solution for the onboard charger, and also you may save some cost on other components. So that's why it's expensive, because usually you have to go for better core material in the passives and better capacitors and so on. So efficiency is also not just a number, because it has to, the customers care about the average of the efficiency across the whole charging profile. So you should not think of it as just a number on the data sheet, but it's a performance along the entire charging profile. So talking about the block diagram here, you can see a simple representation of a two-stage OBC. So at the entrance, you have the AC voltage, which is coming from the grid. So these are the different blocks present inside an OBC. So starting with the EMI filter, which is going to filter the noise coming from the grid, and it prevents it from entering into the OBC, and also it stops the noise from the OBC going into the grid. So in both directions. So PFC is the power factor correction. We will talk about it in detail in the upcoming slides, but power factor correction is just simply aligning the input current that you draw with the voltage. So it makes sure that you're only drawing useful power from the grid, and you're not drawing reactive power or useless power, and it's also a legal requirement. So the EMI and PFC are important because they are also legal requirements, and if you fail to comply to the requirements, you cannot sell the OBC simply. So the DC link is an intermediary stage, which could be a bank of capacitors. So it is going to buffer and decouple. And then this is the DC-DC conversion stage, where the actual power conversion is happening. So in the primary stage, it simply converts the DC that comes from the PFC section into high frequency AC, because the transformer is present, which is needed for providing isolation. The isolation is needed because here you have the AC on the primary side and you have DC on the other side. So this is for safety. And then you have the AC to DC stage, which is a secondary stage, which is basically converting back the rectified AC to DC. And then as a final step, you just smooth out the DC before before the voltage reaches the high voltage battery. So talking about passive components, here you can see there are a lot of components inside an onboard charger, and most of them are passive. So this is a good overview from the website of Yakio. So this is an onboard charger. Here you can see the different blocks. This is based on LLC topology, and it gives you an idea of the different types of passive components that could be present in each block. So One important thing to note when we talk about passives is no passive component is ideal. So when you talk about a resistor, it is not purely a resistor. And likewise, a capacitor and inductor, they are not purely a capacitor or an inductor. So every one of them has some hidden parasitics, and these parasitics will take over when they are operating at higher frequencies. So when we start with the resistor here, you can see that there is a small parasitic inductance, which is coming from the leads of the resistors. And there is also a small parasitic capacitance across it. So when you look at the impedance curve, which here you can see, at the lower frequency range is the only area where you see that the resistor is behaving as a resistor itself, which is what you expect. But when you're increasing in frequency, you can see that the resistor is becoming a capacitor. And when you increase the frequency further, it is no longer a capacitor nor a resistor, it becomes an inductor. So the same component has three different behaviors depending on the frequency of operation. And similarly, this is a parasitic model of a capacitor. So it has a series resistor and inductor. So you can see that above a particular frequency, which is called a self-resonant frequency, the capacitor is completely behaving like an inductor. And then you have also the parasitic model for inductor, also the same. Above a self-resonant frequency, the inductor becomes a capacitor. So this performance is important to understand when designing filters, because then the capacitor is not behaving as an inductor, then the filter might collapse. So the key takeaway from this slide is every passive has a frequency where it is flipping its behavior and it stops doing its job. So that is why when I say a passive is not just a value, you have to know how it behaves across the frequency and not just what is printed on the data sheet. So talking about the first block, which is the EMI filter. So normally, as it is a legal requirement, the component has to be tested for conduction and radiation. So conduction, so also the types of tests are emission and immunity. So in emission, so you basically test how much noise you send out. And in immunity, you basically test how much noise you have to survive. So also there are two paths through which the noise travel. In the conducted noise, they travel through the cables, as you can see here. And in the radiated noise, they travel through the air. So these are the four important tests that will be performed for your device under test. So this is a screenshot of an EMC test chamber. So where you place the device under test inside an anechoic chamber, because you have to isolate from the interference from the other equipments like a mobile phone or laptop. So you can accurately measure how much noise is coming out of your device under test. So here you can see also just an illustration of radiated emission, where it acts as an antenna and sends out the noise, and conducted emission, the noise is basically traveling through the cables. So here is an image from a real test bench. So there is a little buck converter, which is the device under test. So it is connected through these cables to the measurement equipment. So what's happening here is the common mode current flows out and it forms a loop, which is represented by these pink arrows. So this loop of cable then becomes an antenna. So the noise is starting as a conducted problem, and the same cable then radiates this noise into the air. So how can you control is you can control the current on the cables, and then you can also kill the radiation. So which is exactly why so much of the EMI design comes down to the filter and the common mode current. So let's go back to the basics of an electromagnetic field. So here you can see an electric field is generated when a voltage is applied between two plates, similar to a capacitor. So anywhere you have voltage, you have an electric field. and simply a coil of wire, and then you run a current through it, so it produces magnetic flux. So this is a formula here. You can see the flux will grow with the permeability, with the number of turns and the current flowing through it, and the flux reduces with the length. So here is where it becomes electromagnetic. So the electromagnetic behavior is governed by these two equations. So here it gets too much mathematical, but in simple terms, you can understand from the Maxwell Faraday equation that a changing magnetic field is creating an electric field, and the Ampere Maxwell equation says that a changing electric field creates a magnetic field. So what do we understand from here? It means that a change in one is giving birth to the other, and once they start feeding each other, they detach and they travel off as an electromagnetic wave. So they start to radiate. So in the first two cases, we are talking about DC. And in an electromagnetic wave, for example, a ripple or an AC a voltage which is changing frequently, then we are talking about an electromagnetic wave. So the strength of these fields is normally increasing with frequency. So that is why we have a lot of EMI problems when we go for high frequency. So we have our power converters which are switching fast, and they also have sharp edges full of high frequency content, and that is exactly what is turning into radiated and conducted noise. So when we want to go to higher frequencies because we want to shrink the size of our passives, we also must remember to design a very good EMI filter, because this is the root cause for most of the EMI issues. So talking about the two types of noises of conducted emission. So here you can see the differential mode noise is something which is forming a loop in the red arrows. So it flows out on the line and it returns back to the L. To the neutral, sorry. So this is caused by the converter's input current, which is changing frequently, which is commonly called di by dt. And this filter consists of an inductor and an X capacitor, which we will see in the upcoming slides. So the common mode filter, common mode noise is basically flowing in the same direction on both L and N. So this is going to find a path to leak to the ground. So it finds a parasitic, it couples parasitic components and it finds its path to the ground. So this parasitic capacitance is everywhere that you don't want it. For example, between your heat sink to the chassis, between your transformer windings, motor windings, and so on. So that's why common mode is difficult to solve, because it flows through the paths that are not even on your schematic. So the fix to the common mode noise is a filter which consists of a choke and some Y capacitors to the earth. So this is one example of a failed EMC measurement. This is a conducted emission test. And here you can see these dotted lines are the limit lines, which are coming from the various EMC standards. So QP and average, quasi-peak and average line. So this is the spectrum that is generated by the device under test when you do an EMC measurement. And wherever it crosses the line, then you say that the duty is failing the EMC test. So if you fail the EMC test, then it means that you are not passing the legal limits, and therefore you're not allowed to sell the product. So this is an example of a typical EMI filter. So you can see the common mode choke here along with the Y capacitors are helpful to filter the common mode noise. And the differential mode inductance and the X capacitor is useful to solve the differential mode noise. Now, these two differential mode inductors need not be discrete, so they can be they can be used from the common mode choke. So, like we saw, every passive has a parasitic within it. So we make use of the leakage inductance of the common mode choke, and we use it for filtering the differential mode noise. And these are the different protection equipments that components that we have normally for protecting from over voltage spikes. So now let's talk about the X and Y capacitors. So first of all, these are safety parts, even though they are placed in a EMI filter. So when you talk about an X capacitor, it is placed between the line and neutral. So its job is to reduce or filter out the differential mode noise. So the capacitor is designed in such a way that it is always failing short. So if it fails, for example, then you're creating a short circuit between the line and the neutral, and it's going to draw because of the short circuit, you're going to draw a huge current, and then the fuse here is going to protect your equipment. So the fuse is going to trip open and protect your application. So the failure could result in fire. That's why we have a fire symbol here. And when we talk about a Y capacitor, it is connected between the line to ground and neutral to ground to the chassis, and it is designed to attenuate the common mode noise. So this is designed in such a way that it is going to fail open. So because it is connected to the chassis, and it is the chassis is available to the user and they can touch it. So when you create a short circuit, there is a possibility that the current passes through the chassis onto the human body and causes an electric. So that is the reason the Y capacitors are designed to fail open, and the failure of this could result in an electric shock. So this is an example of a part from a Kemet and X capacitor. So here you can see it's rated 310 volts, automotive grade. And the detail I want you to notice that is that it is made of a self-extinguishing material that is meeting a flammability standard. So that's the safety requirement. So because this part is designed to fail in a way that could risk fire, the material itself has to be a flame retardant. So important thing to note is the X and Y capacitors are not ordinary capacitors. So they are safety qualified components with a particular failure behavior, and then you should not substitute it with any normal capacitor of the same value.
Anne, we have a question in the chat. Would you like to pick it up right away or let it be
Yes.
discussed at the end?
Yeah, you can. I can pick it up right now. So is it in the chat?
Yeah, it's in the chat. Yeah.
So how is adding now Y caps attenuating and not creating path for the current flow? So this is explained in the next slide. So I can show. Can you still see my screen?
Yes, we can. Mm-hmm.
Okay, so here I can explain with the help of a common mode choke. So the question is how is the Y capacitor alone filtering the noise? So as I said before, a common mode filter is consisting of a common mode choke and a Y capacitor. So this is the main component. So when you see here, how is the common mode choke helping to block the common mode noise? Is that so common mode choke is simply constructed in such a way that there are two wires wound around a single core. So when both the currents are going through the same way, as I said, the common mode noise here, they are flowing in the same direction. So the common mode noise normally flows in the same direction where I showed you in the previous slide. So when the current is flowing through the core like this, they create a magnetic flux. So because of the magnetic flux in the same direction, the flux is adding together, and this is going to create a strong magnetic field. So strong magnetic field means it is having a high impedance. This high impedance is going to block the common mode current. So some of the energy is going to turn into heat in the core, and that's how the noise will be mitigated. So in simple terms, when the common mode choke is seeing a common mode noise, then it simply acts as a wall, and then it blocks the noise. When the same component sees a differential mode current because it's flowing in different direction, then a flux is created and which cancels out basically, and then there's no resistance. So it simply passes through and it's filtered by the X capacitor. So the common mode choke is therefore the important component in an EMI filter because it's acting as a wall for common mode current and an open gate for differential mode noise. So I hope it answered the question. Okay, and this is also an example of a data sheet of a common mode choke. So the important things to note is basically the rated current range because it's placed on the line. So it has to withstand the line current with margin, and the inductance range, which is also sets how much attenuation you get, and the DC resistance, which is the parasitic resistance that we spoke about. This has to be as low as possible, so you are saving out on losses. And then you also look at the different core materials, which have several advantages on their own, so which will be explained in the upcoming slides. So I will demonstrate do the LTspice simulation at the end. So now going on to the next block, which is the power factor correction. So here is we talk about the famous beer analogy. So when you have a mug of beer, then you see basically you want only the real beer and not the froth. So that's also similar to what the power that you draw from the grid. You only want a power that you can use and not something useless which you want to pay for. So power factor correction does the same thing. So it's a factor which is real power divided by reactive power. It's also a legal requirement, and it has to be ideally unity, which is 1. So, but it's somewhere around 0.95 in the practical cases. So you can see here in the triangle on the right, so before correction, the power factor is 50% and after it is 95%. And how do you correct it? There are several topologies, but the most simple one is a boost PFC. So it's a boost converter. At the same time, it's shaping the input current so it follows the voltage. And that's the PFC stage in our onboard charger. So here the important components are the inductors and also the input and output capacitors. So talking about inductor, it's simply a coil of wire. And here the formula also, which we saw before, and the parasitic model. But the important things to note is what do you look at when you pick an inductor is it should have a low ESR, or which is contributing to the losses most of the time. So when there is a current flowing through your inductor, this resistor is dissipating some heat which is contributing to the losses. So therefore you should select an inductor with a low RDC value. And it should have smooth saturation. We'll talk about it in the next slides. And molded design, which means that it is not radiating more noise outside. The size shall be smaller and the material is highly dependent on the frequency range. So coming back to the structure of a magnetic component, it's simply a wire which is wound around a core. And again, the formula is important to remember. So when we talk about, so we spoke about AC, which is the area of cross section, N is the number of turns, and L is the length of the wire. But this mu naught and mu r are the permeability constants. So what a permeability is. So a higher permeability material means that your material can hold the magnetism better. So it doesn't let you get more inductance. It lets you get the same inductance in a better package. For example, when you look at this equation, you can see if you simply increase the higher to a higher permeability core, you can trade that basically with something useful. So you can reduce the cross section and the number of turns. So you're saving some space on the board mechanically. So this lets you use a thinner wire while keeping the same DC resistance. So higher permeability materials could be, there are different types of materials of the cores like nanocrystalline, manganese, nickel, zinc, and so on. So each of these materials have specific advantages over the frequency range. So simply when you increase the permeability, you can use that gain on reducing the area or the number of turns. So the different types of losses, the DC copper loss that we spoke about, which is because of the heat generated in the parasitic resistance in an inductor. So AC copper loss is normally at higher frequencies. We have something called skin effect. When the current is not flowing through the center of the conductor, it's flowing on the surface of the conductor. So this is called skin effect. So in order to reduce the loss of the copper with AC currents, then we have to have a flatter wires. So there's also something called core loss, which is the loss of the magnetic material itself. So that is the BH hysteresis loop. So it is also growing with frequency, and the area of the hysteresis loop shall be as small as possible to reduce the loss. So when you talk about the total loss that will happen in a single inductor, then it's simply a sum of all the different types. So also something important that you have to look at is the saturation characteristic. So the inductors could have hard saturation or a soft saturation. So here you can see the value of the inductance is not constant. So it's changing with the current that you pass through it. So here you can see the hard saturation. The curve is not holds. It's not fairly flat. It's changing rapidly. So this is dangerous because if your ripple current is swinging into this region, the inductance can change unpredictably, and the current can also spike. So on the right is the soft saturation. So it's the same idea, but you can see the ripple is not changing very abruptly. So it's stable and predictable. So if your application has high ripple currents, then you normally should prefer soft saturation. So this is going to keep the inductance value stable and well behaved. Now is the material comparison that we spoke about. Here you can see different core materials. So the manganese zinc series. So here we are talking about the permeability, the mu that we saw in the formula. So the permeability change with respect to the frequency. So when you use manganese zinc component, you can see it is having a good noise suppression effect in the low frequency range. But when you want better attenuation in the higher frequency, then you go for nickel zinc series. So it doesn't offer a higher inductance value, but there's a trade-off. And the behavior of the inductance with respect to the DC current, here also you can see the manganese zinc ferrite is dropping very abruptly, but the metal composite is pretty stable. So the takeaway is the ferrite core is going to give you a higher inductance value and a smaller size, and it's also stable. But the metal composite is going to give you a very stable saturation across a wide range. So now we go to the DC link, which is the capacitor, which is acting as a buffer and a decoupling. So there are several different types of technologies, so which are based on the voltage rating and the value of capacitance that you will need. So for DC link, the most popular technologies would be film and aluminum electrolytic, but nowadays they're also using ceramic. So this is already explained. So DC link is basically an intermediate stage between the PFC and the output stage. But so what does it do? It does two important jobs. So first one is it provides a low impedance path, so it can allow the high frequency content to pass through it like the noise. And the other one is a buffer. It's going to smooth out the DC voltage. So in our onboard charger, this is something which is sitting between the PFC and the DC-DC stage. So here you can see different technologies that you can use. This is a film capacitor, and this is an aluminum electrolytic capacitor. and some design considerations for DC link. So you can see that when you're using the capacitor above its rated voltage, the lifetime is going to drop very abruptly, and it's a comparison between different temperatures. So you should not only look at a particular value of lifetime at a temperature. Instead, you should always look at the graph, and you use a chart like this to get the lifetime that you will need for your application. So especially this is important for automotive, because you need to have a 15 years lifetime of your product. And also power dissipation, because there's something called self-heating of a capacitor. As explained, this is due to the ESR. So the ripple current basically is going to cause the internal heating of a capacitor. So it is also going to depend a lot on the surrounding temperature of the capacitor. So you can see here that the capacitor is tolerating full 30 degrees of self-heating and lots of ripple current. But as the ambient temperature is rising, then it's losing the margin. So it's going to fall off soon. So this is a summary, which I will skip of all the topics that we explained so far. So there are two focus areas on basis of which you can choose the type of technology. So if your focus is just the value of a capacitance, so these are the requirements. You want to have 1 millifarad capacitance with an application voltage of 500 volts. So your focus is only on the capacitance. So how will you choose between these two components? You have a film capacitor and an electrolytic capacitor. So for the same value of capacitance, you need the volume of the electrolytic capacitor is very small. And for film is 841 centimeter cube. So therefore, the electrolytic capacitor is always better when you want to have a cheaper solution and also a lesser volume solution. But when your focus is on the ripple current, the requirements are going to be completely, the choice is going to be completely different. So here your requirement is 15 amps at 10 kilohertz. So to meet this ripple current, the film capacitor is going to need only one component, whereas your electrolytic is going to have need 5 components. So when we focused on capacitance, the electrolytic was smaller and cheaper, but now on ripple current, the film capacitor is going to be better, also volume-wise, because the number of components are less. So nowadays, there's also a trend that ceramics are used as a DC link because of the fastest higher frequency of switching converters. So ceramic capacitor is giving you less capacitance when compared to film or electrolytic, but in return, there are also some advantages that it can offer. So it has a higher dV/dt withstanding, and also it is going to support wide-bandgap semiconductors and offers a higher frequency behavior overall. So it doesn't lose its capacitance as the frequency is rising when compared to the other technologies. So there we see a trend that nowadays ceramics are also widely used as a DC link. So now coming on to the actual conversion stage. So normally we have unidirectional or bidirectional, but nowadays bidirectional is getting more popular because there are more demands on your charger. So you want to use your onboard charger to charge, also to send power in both directions. So this is also what is needed for V2G, V2L applications. So therefore, these topologies are highly replacing the unidirectional topologies. But today we'll talk a little bit about LLC. So LLC is the main concept behind the resonant converter is the electrical resonance. So what happens is at a particular frequency, the reactance of inductor and capacitor is going to be the same. So at this frequency, it's behaving as a resistor. So the capacitor and inductor are going to disappear from the picture when you look at a series RLC circuit. So here you can see at the high frequency range, the inductor is dominating, and here the capacitor is dominating. So you have to also understand that the components are chosen in such a way that they have to withstand the voltages which is based on the high frequency operation. So this is an LLC converter. Here you can see the tank, a resonant tank. So this is going to convert the square wave on the left. The square wave is feeding the resonant tank, and the tank does something different. So it is going to filter out the harmonics, and it hands over clean sinusoidal voltage. So the converter is running on smooth sine waves rather than harsh, switching edges. So this tank is important for the operation of LLC converter because it is setting the gain versus frequency. And instead of changing the pulse width as in other modulation techniques, the controller is regulating the output by simply switching shifting the frequency around the resonant point. So here, if you see the curve on the right, so this is the resonance peak we built up to, and for different Q values. So a higher Q means it gives a sharper and taller peak. So this is where it connects back to the passives because the value of resonant frequency is 1 by 2 pi over LRCR. So it's depending on the values of the passive components. So if let's assume if there is a 10% error in the resonant capacitor, then it's going to shift the whole curve by about approximately 5%. So that's why the resonant capacitors and inductors shall be a most precision components. So at resonance, the voltage that the component see is Q times the value of the voltage coming from the source. So it means that they should also withstand voltage which are much higher than the input voltage. So talking about wide-bandgap semiconductors, which is a hot topic right now. So we have silicon carbide and gallium nitride. So the speciality of these components is that they can reach a place where the silicon simply cannot. So gallium nitride is basically opens up the high frequency range, higher voltages and higher temperatures and higher power. So we have three benefits. So first one is the high frequency, voltage and temperature. So it also means you have low ESR and low ESL, which are the parasitics. So simply the wide bandgap doesn't just improve the switches, but we also need several well-designed passives around them, like the snubbers, for suppressing the high DVDT, which is coming out of the switching. So why is everybody moving to high frequencies? So the wide bandgap semiconductors are capable of switching very fast. So you can raise the frequency. But what happens when you raise the frequency is that the inductors and capacitors can become small. So when they become small, then you are reducing the entire mechanical dimensions of the product that you have. In our case, an onboard charger. Then it is just because at higher frequency the components have to only store some energy when compared to lower frequency. That's why the dimensions, the components itself are becoming smaller. So small passives means you have higher power density, lesser weight and lesser copper, and also you're lowering the cost. But however, when you're shrinking and when you go for higher frequency, then you also have more EMI noise, and you need to design your filters well. So why is again everybody going to high voltage is because at higher voltage you can basically reduce your current to half. So when you reduce the current to half, then you need then you do not need so much copper, because your cables can become smaller and you can have reduced weight, and you can save on the losses and the cost and so on. So this is why everybody moves to higher voltage. So how do you choose your capacitor when you have a wide bandgap converters? So you should check for the voltage rating, the frequencies, because especially as we saw in the parasitic model of capacitor, it's completely changing its behavior when the frequency is changing. So you have to look for the entire impedance curve and see the capacitor is working as intended. And higher temperatures, more than 125 degrees Celsius, is also essential to look at. So normally when we look at some capacitors, they are rated for temperatures of 105 degrees Celsius. It's most common. So when you work with wide bandgap semiconductors, then you have to make sure that they are also operating well at 125 or 150, as the typical operating temperature range in automotive is also 140 degrees Celsius. So you can use, there are several types of dielectrics and of a capacitor. So the most common would be polypropylene or COG. So here also several examples of snubber capacitors, which is placed basically across the switch to reduce the transients, also in the resonant tank and the filters and so on. So you look at most important parameters here before you choose the right component for your application. And talking about isolation requirements, so because the high voltage battery is it's high voltage and it could be harmful if there's a leak or a leakage to the surface. So to prevent it from creating a shock hazard, so you need to take some design considerations like the clearance and the creepage. So this is normally mentioned in the standards for high voltage systems. So creepage is the distance over the surface. Clearance is the distance through the air. So this is the distances are mentioned in the standard, and you have to take care of it when you are designing. And talking about insulation, so we also have three different types: the functional, basic, the double insulation, which is basic plus supplementary, and reinforced insulation. So I like this analogy with the coats. So a t-shirt is normally just to cover a body, it's serving the functional purpose. And when you want to provide double insulation, you have a sweater and a coat, and reinforced is a down jacket for warmth. So these are also mentioned in the requirements from your customer to comply to between different circuits in your product. So emerging trends. So as we spoke about before, we have vehicle to house. You can power your house with the EV. You can also send back the power from your car to the grid when you have some during peak hours, and you can get paid. And this is V2L, where you can charge basically from your car to any load like your laptop or something else. And some other trends that are coming up is integration. Something interesting that I noted is this product from Geely, which is 16 in one intelligent e-drive. So it means 16 separate power electronic components are placed in one integrated unit. So instead of a car having an onboard charger, DC-DC in separate boxes, so this is an integrated solution which is sharing one housing, one cooling, and the same connectors. So why do people talk about integration is basically all the reasons that we talked about so far. It's the space, it's the weight, and the cost. So when you integrate everything, all the components are sharing the same systems basically. So also the control electronics. So you can eliminate redundant cases and cables. So it's a challenge also integration creates, because when you pack all the converters into one space, then the passive components inside, they end up getting heater and closer together, also creating more noise, and it's also making challenging also to design circuits with passives. So it is increasing the demands on all passive components to be more effective. So before we go to the summary, I would like to show a simulation of LTspice. I will reshare my screen shortly. So this is a circuit, a simple EMI filter. Here you can see the common mode choke for common mode filtering, and the leakage inductance for DM filtering, and also the Y capacitors and X capacitors. So here you have two different circuits, one with a damping resistor and one without a damping resistor. We will see why they are important soon. And here is a circuit with a parasitics for each component. So here they are just ideal components. So we can see how the behavior will differ based on, yeah. So first we have plotted the transfer function between the first one, which is without the damping resistor, and the blue one is the transfer function with respect to frequency with the damping resistor. So what you can notice here is that the green curve is attenuated to around 12 dB at the corner frequency, which means that you are basically amplifying the noise that you want to filter. So which is undesirable. So when you have a damping resistor, then the peak is dropping to about 9 dB, and this is giving you this is damping the attenuation amplification that you are doing without this damping resistor. So the same filter with so again, this damping resistor, you're trading basically with the high frequency attenuation, because here you can see the I do this. So the green one is without damping resistor. You see that it's providing much better attenuation than the one with the damping resistor at high frequency. So again, it's something that you're trading for. And now let's compare with the one with the parasitic components, and you can see a different behavior. So it's not in real world, it's not functioning as perfect as you want. So here you see up to 20 kilohertz, it is on track. Of course, there's a small notch here and it drops. So at around 28 kilohertz, there is a notch. So this is because of the capacitor, which is resonating here, the output capacitor resonating here with its own inductance. So after this frequency, it's an inductor, and then you can see the attenuation is collapsing. So of course, if you compare it, then you can see an ideal filter has a smooth attenuation across the frequency range. But when you look at a real component with parasitics, then you see the behavior is changing. So when you're designing an EMI filter, then you design it according to your application, because you know that at which frequency your EMI test is failing, and then you choose the component values accordingly. So coming back to the PowerPoint. So to summarize what we spoke about so far, the onboard charger is the vehicle's only AC to the battery path. When you do a DC charging, it's directly going to the battery, and it's bypassing the onboard charger. And talking about the passive components, why they are important, because roughly 40% of the volume inside an OPC is the passive. They contribute to around 38%, and also 30% of cost comes from these. So EMI is a system problem. So the differential mode noise is something which is coming because of the schematic, and the common mode noise is something which is happening because of the layout and not your schematic, because of the coupling to different things that you cannot expect. And every block is leaning on its passives for better efficiency and losses and so on. So you move to higher voltage and also to higher frequency, so you can buy some efficiency and also power density. And when you go for wide band gap, you can effectively operate at higher frequencies, and you can shrink the size of the passives, but at the same time, it's increasing the EMI problem. And talking about the trends, you have V2G, V2L, X, the bidirectionality, and integration, which are the key design factors which influence the design of onboard charger in the upcoming days. So that's all I have for today. I hope the webinar was informative.
Yeah, thank you so much, Anne. We have quite a lot of discussion in the chat.
Okay.
So maybe we will jump into that
Yeah.
right away. I think we have several questions raised and some discussions ongoing with the comments partially. So maybe just take a moment and go through that.
Okay.
So we have some questions from Vasudevan Ranja. He's been quite active. So maybe we could start with that one.
Okay.
Regarding the passive PFCs, an option in OBC, or only active PFC are always considered, and why?
So I actually don't see the question.
Do you see the chat?
Yeah,
Let me
I see the chat.
let me
Maybe I start from
refresh.
the last question.
Yeah,
Yeah,
sure.
I think
It's
that's
up to you. Yeah, I am sharing my screen again so you can see the chat basically.
yeah. So the last one is what about the output DC link capacitor with the single stage OBC? It's already in Tesla Cybertruck. So what I know about this is Tesla is having a matrix topology where it doesn't need a DC link at all. So yeah, this is gaining quite a lot of popularity at the moment because DC link, the entire stage is removed. So I'm not sure about the filtering in general, but I know that the DC link stage is eliminated. How can Y capacitance be reduced by keeping the common mode in check? Okay. It's undesired because of the discharge hazard. Yeah, so normally the Y capacitances are designed starting from one requirement, which is the leakage current. So when you talk about designing, there's a common requirement that you often get that the leakage current shall be only 3.5 milliamps. So you start from there and then decide the value of the Y capacitance. So when the isolation is breached, reinforced isolation is often problematic in terms of cost and space. I think it's more of an information than a question, I think. But the first part of the question is answered. It's normally started from the leakage current limit. So from Kiran is a question, how did you choose these damping component values? So it was just an approximation. I put 10 ohms as a damping resistor to the 10 microfarad. So it's just an approximate value. So commercial OBCs or any converters that are sold mostly use active PFCs because you can seamlessly control power flow using the MOSFETs and achieve high. Okay, this is also not a question, but an information. It's fine. So it is an open loop control. No, LLC, what I spoke about is closed loop. So there's a feedback and it's controlled digitally with the controllers and then the frequency is set. So control lookup table with voltage control oscillator. Yeah, this is also an answer, I suppose, to the question before. Yes. So I
All
think
right.
it's most of an interaction between
Yeah.
questions.
Cool.
So
Quite a bit of interaction. Yeah. Right.
yeah, yeah. So it's not a straight question, but an interaction, as I understand. Okay.
So we have, I think the last one from Shubham just arrived. If there will be a flyback converter deep dive with control loop in future. Maybe it's a question for Annie if she is like
Okay.
willing to prepare something
Yeah,
into
yeah.
that
Definitely,
direction.
we
Yeah.
can work on
Then
something.
we can
Yeah.
organize something. Yeah. In the near future.
Yes.
And yeah, you can get the recording after the webinar. So someone was asking that as well
Mm-hmm.
in the chat. So I think I will just go through the remaining slides now. So we have, of course, some useful things for you left. So you can see you have an option to get an online course on any of these subjects that we have on our platform. So you can use some filtering as well. You can check it for yourself using that URL, wide.com/courses, and you can see every power electronic related stuff there that we have. And of course, for all the webinar attendees, we will provide you some additional goodie. So it's wide 10 as a discount code. You can use that and you can get a 10% of the price discounted. So also some useful thing, I guess. And of course, if you would like to work on your LTspice model or any other, let's say, power electronics related simulation or power electronics software tool, you can use private tutoring on our platform, and you can basically use the filtering and see which experts we have in the electric circuits designs, and you can basically schedule a call with that expert and discuss your particular task. Or you can also, if you feel comfortable and experienced as an engineer in that subject, you can join the platform as a member, as a partner member, and you can give your tutoring yourself for our customers, for our students. Anyways, you can check the URL wide.com/members later on and explore all the options. And I would like to thank you all for your time, for joining today. I hope you enjoyed that. Thank you, Anne, so much for giving the speech. Very well prepared. A lot of material. You have around 60 slides, I think, also with LTspice demo. Huge thanks to you. Very well organized. Looking forward to the next sessions with you. Um, and maybe some final words, if you have something to say, Anne, from your side, your feedback or some motivations
Yeah.
for.
Yeah, thank you for listening. And there are a lot of questions in the chat, so which means people also actively listen. So I'm happy, and I hope you took something out of this webinar. Thank you.
Yeah, absolutely. Thanks a lot, Anne, once again. Looking forward to the next session with you. We will do the processing of the video recording and we will publish it and we will share the recording and all the presentation slides after the webinar via email. So we will send it around and you will get all the recordings and the PowerPoint presentation. And if you need a certificate, you can also request that and receive a certificate as an attendee. So thank you so much once again, and I'm looking forward to the next one in the future. Thank
Thank
you.
you. Thank you.
Bye bye.
Bye.